Hey, this is OXDF, and today I'm looking at Hackvent 2022, Day 21, Santa's Workshop. So for this one, I'm given a binary as well as a Docker to spin up and connect to. We can connect to it. I just wrote down the address here. It's on 1337. And we get welcome to Santa's Workshop. We can view the naughty list, and it says like tell me an index. And if we pick 1, it's like flag sharer. If we pick 0, it's flag hoarder. 2, it says guessy challenge author, and we can, if we try like 3, it says I can't show you an entry that doesn't exist. So we're back at the menu. We could check the workshop for items, and it has some items. We can steal presents, and it says you tried to steal something, closing down the workshop now. If we go back to the workshop now, I believe it's going to just crash us out of here. Yeah. So we come back here. And the last one was like, tell us a good deed. How long is your deed? We'll say it's like 20. I made a YouTube video, but then it just disconnected. So I believe the instance is set up so it only runs for 30 seconds before it cuts you off. So with that, we do have this Santa's Workshop.elf. We can run it, and it does the same thing. We can look at it. It's a 64-bit elf file. Not much else we need to know there. Yeah, so I think the first thing we're going to do is I just opened up Ghidra. Haven't even made a project for it, so we'll make a project in this directory. I'll Ghidra and call it Hackvent 21 or 22. Yeah, 21's fine. Let's see, we might need to make this directory. There we go. So let's use that and finish. And then we can Control I to import from this Santa's Workshop elf. That's weird. Let's try that again. Let's go up here into the Hackvent 22, 21. Okay, worked fine. Not sure what happened the first time. We import it and we can look at it. So, there's one other thing we should do before we look at it. Well, while that's loading, we can do Checksec on Santa's Workshop.elf. For some reason it doesn't. There we go. And so we can see that full relro, canaries, not execute, and pi are all enabled. I'm going to assume ASLR is also enabled then. So we're going to need to overcome those things. Okay, let's give this an analysis. Analyze, we'll just use the default. And it's done. We'll come here to functions and check out main. Good place to start. So basically this prints out the menu stuff. It does this init on context, which is kind of interesting, and then it calls menu. If we check out init, it's creating a 48-byte or hex 30-byte buffer called workshop. That's a global variable. It then copies in 28 bytes of this stuff we saw when we ran the workshop, and then it copies the print function, or this print function, into workshop plus 28. We can see this print just prints workshop, the string in workshop. So that's a little strange. We'll definitely want to keep this in mind. Let's see. We'll come back here, we can go look at the menu, and we'll see actually if we put in a 2, that workshop is actually calling the function at workshop plus 28. So that's right there, that's like a pretty interesting target. Like if we can figure out how to change that function to something we want to run, then we can just call 2 and run it. We will look at the steal one next. Let's take a look at this. And all this does is print some stuff and then sets that workshop print function to dead code, which is why when we tried to run it after we ran this, it crashed. And then it frees workshop, which basically says, tells the program, the memory associated with workshop is now back available for use on the heap. But what we did not do is necessarily get rid of our pointers to workshop. So this is clearly an opportunity for a use after free. Let's see, let's look at tell deed. So tell deed, we can do some quick looks at this, but so it's putting out how long is your deed. It's going to then read in. Let's see, we can look at this. We look at this global. It's going to read in a ZU. Rename global %ZU. So it's going to read an integer or an unsigned number into local 20. User submit it user length, and then it's going to check. It's going to see. Let's see. This will be num red. So it's going to read in as long as num red is 1. It's going to make sure the length is between 0 and hex 32. Otherwise, it's going to say it's not right. And then it's going to say, give me the deed. It's going to malloc something. So it's going to get some. It's going to get a buffer from the heap. And say rename variable deed buff. And then it's going to read into deed buff the user length. So it's going to read from standard input. It's going to read from me, and it's going to write it in there. So we have the opportunity. We saw that use after free potential. If we can then tell this malloc to get the same size as workshop, there's something there. We should look at that. Let's see, a couple more things to look at. Coming back. Oops, there we go. We can look at naughty. So this one, let's see, let's do some renaming. This has canary up front here. Anytime you see this fs offset plus 28, it's getting a stack canary. It's got some stack strings here. And it says, tell me an index, I will show you the entry. So this will be rename user input is rename variable num red. So as long as the user input is less than 3, we're going to go get this local bit buff. So we'll call this like strings buffer plus the user input, only the first byte of the user input times ox1e. So that's what's going to get us, 0, 1, 2, and then anything else is not accepted. And then it checks the canary again and exits. There is one other function we can look at. If we come over here to the symbol tree, we'll notice that we've looked at init, we've looked at main, menu, present, print, steal, and tell deed. We've not looked at present. So if we click on that, there's a function called present that's not actually called from the main menu, but it just gives you a shell. And so that's a good target, right? Let's talk about our strategy then. We want to overwrite workshop. And so first we're going to use the steal function, which is going to free the workshop memory. Tell the heap that memory is up for grabs again. Then we're going to call tell deed and ask for a deed of ox 30 bytes or 48 bytes. And it's going to say, oh, the top thing I have available is this thing I just got back, so I'll give you that. And we're going to write into it 28 bytes of whatever, followed by the address of present. Now, with pi/ASLR, we need some way to figure out where present is. And so we're going to need to find a memory leak. And that's where we're going to use naughty. We'll come over here to naughty. Naughty checks to make sure your input is less than 3. What it doesn't do is check and see, what happens if I put in a negative number? In fact, we can try this. If we run naughty, and then we run like negative 200, it prints nothing, but it tried, it didn't error out, it tried to read something, right? So we can eventually, try, it might crash eventually, but it's trying to read something, and it might even be reading something. We can check here. We could well, anyway, that's fine for now. We'll go with that. So we want to plant something. We want to see what we can read. And so we're going to have to figure out how to use this to leak out useful information. So, yeah, our exploit program is going to look like that. We're going to connect in. We're going to run menu 3. Then we're going to run menu 4 and write ox 30 bytes with a bunch of A's or something, and then call, and then the address of present. And then we're going to, after we leak that address and calculate it, we can do that. So let's do a few experiments to see how this is going to work. The first experiment we can do is, I'm going to open up a new window here, and we can do GDB, Santa's workshop. So we will put, what we're going to do here is we're going to check and see, does that use after free really work? And so we can do something here where we let's just say run. So the first thing we want to do is 3 to free the memory. So it's closed down the workshop. Now if we do 4, and it says how long is your deed, so we'll put in 48. It tells me the deed. So let's do 1, 2, 3, 4, 5, 6, 7, 8. And I will copy, so that is now 16, 24, 32, 40, 48. It says, cool, maybe you get a flag. Now, let's check the workshop for items. And we crashed. And we crashed because we're at a call RDX. And if we look at RDX, go up a little, right here, RDX is my all A's. So we have effectively put that in. We could run this again. Oops, I got caps lock on. Run this again. We can clear, free the memory, do a good deed. 48, 1, 2, 3, 4, 5, 6, 7, 8. So let's try, just to prove a point. I can do this. I can do, there's 16, 24, 32, 38, 40, 2, 3, 4, 5, 6, 7, 8. Now we've just changed those last words. And so now when we run 2, we crash at RDX, and RDX is all B's. So we've shown basically we can control EIP. We can make this jump wherever we want. So now all we need to do is get the address of present. The problem is, so we can do like print present, and we can see it is at all these 5s, 40, OX, 98, right? The problem is with Pi and ASLR on each start, this is going to change. So how do let's figure out how we're going to find the memory we need. Let's do a disassemble on naughty. And we want to look what we want to look at? We want to look at the memory in the buffer that we're reading out of. So here's this scanf is where we read our input in. The results, let's see. So we can see right down in here. Let's put a stop point right here. So we'll do break right there, and we will run, and we will put in a deed, and we'll put an index of 1. And we can see we're at this point. We are going to move RBP plus OX78. I'm going to make this a little smaller here so I can fit more on my screen. Into EAX. So we have EAX now has 1 right here. You can see that's the... can I go any smaller? I don't know if this... You all have to yell at me if this is too small to read. But you can see our RAX is now 1. And we're going to move AL, that's a low byte, into EAX. That's if we had sent a big number, it would chop it down. The next instruction here is going to load the address of RBX minus 70, or RBP minus 70. So that's going to be our buffer. And that loads it into our CX. So you can see that's where we have flag holder. I might go bigger again here. We can do something like X32XG on that address. Oops, is that the address I wanted? Let's see. We'll do $RCX. And you can see here is the first flag hoarder runs through this. If we go 1, now remember what we do is we multiply by 1E. So that's not quite 2, it's going to be 2 bytes short of the next one. So that's actually going to be these 2 here. This might actually be easier if I do as bytes. It's paging, but okay. So we can see here, here's 8. Here's our first one. This will be 1. This will be 1, 8. And so 2 would be down here. So right here at the end is where we come 1E. Now if we go 1E from there, it would be down 1, 2, 3, 4, and back 2. So it'd be here. We go 1E from here, down 2, 3, 4, back 2. So this is just like a big null word. Down 1, 2, 3, 4, back 2. Then we get this word right here, etc. Now, we got to figure out what's the memory space we're looking for, so we can quit this. If we do info, what is it? It's info memory? No, that's not quite right. Oh, info proc mappings, maybe? Yeah, there we go. So we can see we're looking for a function that's in Santa's workshop. I actually didn't notice the present function at first, and I spent a long time trying to find a way to leak some address of libc, which, if we come back up here, so we'll note libc basically now is running from 7 4f 7d through 7 4f 7f, something like that. There is one here, right here, that would be a very valid leak. The problem is it doesn't actually fall on a multiple of 1e, and it's actually really hard to get this out. So we want to find something that's in this range right here, because this is where we want to find. So a bunch of 5s, 4 through 6, basically. And if we come back up here, we can see, looking at it this way, here is a bunch of 5s, 4, 0, 0, C93. Now with ASLR, these last 3 are not gonna change. So we're just gonna randomize this stuff, or with pi, I guess in this case. So if we can get this address, we can calculate the offset to the present function in our current memory space, and that offset will be the same in the other memory space. So the question is, can we read this? And we noted that it was 4 off, right? 1, 2, 3 puts us here, and then 4 puts us right here at the beginning of this. So we're 4, we want index number 4. How are we going to get there? Well, we want to build something. We're going to build go in here, I'm going to run Python. We want to build a number that is a negative number that looks kind of like 4. So my idea was to say, well, if I take the number 1 and I shift it 31 spots to the right, that'll be like 1 followed by 31 zeros. Big number, right? Now I'm going to add 4 to that. And this is the number I want to get put into, this is the number I want going in, because then when it ORs that, or ANDs that with OXFF, I will just have the 4 left, right? Now this is a big number. In signed, what I'm going to do, to make this a signed number, I can subtract POW to the 32nd. I thought I could subtract, maybe I might need am I missing a parentheses here? There we go. So this one up here was not quite right. We'll need to do, apparently it was shifting it by 35. There we go, that looks better. And so if we want to make that a signed number, we make it that. And now we have a signed number. Let's go ahead and test this. Let's put this in. Back in GDB, we will run again. We will tell a good deed. Nope, we don't want to tell a good deed. We'll run again. We will view a naughty list. The index we want to put is that, and we break. So I'm going to make this smaller for a second so we can track it. When we read, we're going to pull the number into EAX, and you can see here we have 8 and all 4s, right? All 0, 0, 0, 0, 4. And then we're going to chop it, and now we have 4. And then we're going to load into RCX, the address of the buffer, flag quarter, you can see it. We're then going to move EAX into RDX. Not sure why, but okay. Now we're going to move RDX into RAX. Okay. Shift right RAX times 4. Subtract some stuff. Let's see. Oh, I see. And then add it again. We're basically, this is a complicated way of basically doing the multiplication times 1e. But if we get that, when we eventually add these all together, you can see we're pointing at that memory space ending in C93. So that is awesome. In fact, if we continue, it prints like at UUU because it's not intelligible. I guess U is 55. So we can leak this, and that's what matters, right? So now that we have the pieces we need, let's build this. So we'll say vim, make this a little bigger again, solve.py. We'll start with our shebang, Python 3. We will from pwn import star. We're also going to import sys, so I can pass it my address pretty easily. R equals remote, sys.argv1, comma, and the port is always 1337. Okay, so the first thing we need to do, we'll make a thing down here so we can try it. We are going to r.send line after, and we're going to say after we have this prompt here, actually with a space, not that it matters. We are going to send the line bytes 1, because we're going to go ahead and do our leak. Now we will r.send line after. And so if we come down here and push 1, oops, not Q, 1. The next thing we need to do is tell me an index. So our index is, I'll show you the entry. Let's see, so we'll get this. Be like that. New line, and then what is the thing we want to send? So we want to send I guess it's just going to be, where's my negative number? This. Like that. Cool. So we send that. Now we're going to read the response. So we'll do r.read until, and we're going to read till we get back to this, I believe. Paste that and make sure. Surprised we didn't get anything on this one. Maybe my memory space is different, so it's not actually showing fives. Certainly possible. So it's just, this shows you maybe I do have ASLR running and I just don't have it working in GDB or Pi. So you can see we want to read, we don't know how much we're going to read, but we want to read up through this thing. So we'll read that, read up and through that. Now we can say we can calculate our pi leak equals, and we're going to take res and, well, actually we aren't quite sure what we need here, I guess. So let's do just that. And we will now python solve.py with a -i. We run and our index is out of range. Of course, we need to pass it our IP address, which is somewhere near here. There we go. We're connecting. We have this. So what does res look like? Cool. So we have res. We don't want this new line and we don't want this thing. So we're going to say res up to the last 2. Nope, up to the last -2, like that. And now we can say use 64 of that to turn that into a number, an unsigned 64. Ooh, it takes a buffer of 8. Okay, we'll take this and we will dot ljust this to 8 bytes ox00. So we'll put some nulls on it. And now we have a number. If we p64 that, we get back our bytes. So this is what we're looking for here. Or if we, probably a better way to do this, but if I put it in colon x like this, I can get it as a, no, I guess I guess we could say, anyway, not important. So we've got our thing here. Let's go up here and say, so we'll say pi leak, PIE leak equals, and we want, where do we want here? This right here. Cool. Now we need to figure out, let's see, present address equals, let's go back to our GDB. So here we are here. We want to know, I guess we can run, do our leak. Let's get our negative number. Paste that in. That's not the right window. That's the right window. So what we want to know is, what is the address that's leaking? So get that address in here, right here in RCX. So we can do x32xg $RCX, print that memory. So we want, okay, we definitely have ASLR going. So we can do RCX plus 1e times 4. I wonder if I can do that. This might not work. Oh, it did. Sweet. Okay, so we have this address right here. Yep, that's our address. Now we want to know what's the address of present. We can print present, and we can see it's right here. So we can do print this minus present. Nope, not like, doesn't like that. Let's do print that minus that. 309. So whatever we leak minus 309 will be present. So come back here. We can say pi leak minus ox 309, and now we've got the present address, and we can even say it. Let's say it. Success found present address ox 08x. So we can now run this, and we found a present address. If we want to be like nice and cute, we can add like that. Okay, So now we got the present address. Now the rest of this is actually pretty simple. We've already read in the next prompt, so let's go ahead and send. We want to free the workshop, so now we can say, let's say, free workshop, and maybe add some comments here. Leak present address, and free workshop is just going to be as simple as r.sendLine bytes on 3. Next thing we need to do is reclaim that heap allocation. So claim heap allocation, and so we will payload going to be equal to, I'm just going to make it like oxdf.ljust, and we want this to go 40 bytes. So we can do ox, we'll do 20, we'll do to 40, and then we can do ox nulls, because it seems like a good place to end that. We'll make this into bytes plus p64 present address, like that. So now we can r.sendLine after b when we get back to this again, and what we're going to send is 4. So now we're ready. We're making ourselves. We've said we're going to put in a deed. We can come down here and check, make sure we get that. I guess I didn't. See, we'll run it here. We're going to tell a good deed. How long is your deed? We'll have r.sendLine after b. Indeed, new line like that. And the next thing we're going to send is we want to send 48 bytes. Okay, so then we can do r dot, so we'll add that here too. Okay, tell me the deed. Send line after b, deed, new line, and this time it's just going to be payload. And now, presumably, we've now overwritten the function that gets called, so now we just need to call it. So trigger, we'll do r.sendLine after this, and we want to send 2. And then we will r.interactive to interact with the shell that we hopefully have. So let's give it a run and see what happens. We've got a shell. Pretty sweet. We can from here, if I remember correctly, it's under challenge. Took a minute to find this, but in challenge we have flag, and we can cat flag, which gives us a nice ASCII art QR code to get the flag. So I thought this was a pretty neat challenge. I really enjoyed it. It does a good job of exposing some of the ideas of heap exploitation without having to make, like, this is a pretty toy problem, right? You're not going to just have random buffers left open like this that you can just override a pointer and call it. It's usually a little bit harder than this, but this is a good kind of beginner level heap challenge, which a beginner level heap challenge is still hard for most of us. So with that, I'm going to call it here. Thanks for hanging out with me, and I'll talk to you next time. Bye.